Yesterday's thermal conductivity instruments typically limit characterization to a narrow range of sample materials. The samples are often forced to adapt to the instrument's rigid requirements, rather than the instrument adapting to the sample and application needs. Trident by industry leader Seetherm represents a new paradigm in thermal conductivity measurement, delivering 3 of the most powerful transient methods in one instrument. It's better to have options. Built on Seetherm's reputation for world-class thermal conductivity instruments, Trident is dynamic and satisfies the most prominent ASTM and ISO industry standards. It combines the precision of MTPS with the flexibility of TPS and the robustness of TLS, all in one modular package. These options support a wide range of applications without sacrificing ease of use. Trident meets the needs of today's labs and is future-proof for the challenges of tomorrow. The MTPS, Modified Transient Plane Source method, employs a single-sided sensor to directly measure the thermal conductivity and effusivity of materials. The method features the highest precision and sensitivity, providing accurate test results in seconds. It offers the maximum versatility for the non-destructive testing of solids, liquids, powders, and pastes. It is adaptable for high pressure, broad temperature ranges, and environmental conditions. No regression analysis is required. MTPS is the choice method for situations where reproducibility amongst multiple users matters. With a double-sided sensor available in different sizes, the Flex TPS Transient Plane Source method provides researchers the greatest flexibility over experimental parameters, including timing and power. It is recommended for more experienced users with specialty slab, anisotropy, and thin film modules available. With no contact agent required, the hot disk-style TPS sensor is ideally suited for polymers, compacted geological samples, metals, concrete, and asphalt. Flex TPS is ideal for experienced researchers looking to push the boundaries in thermal conductivity. Sheathed in stainless steel, the TLS, Transient Line Source Needle method, offers maximum robustness in thermal conductivity testing. TLS is best suited for granular materials, polymer melts, soils, slurries, and gels. Seetherm software provides full data acquisition and analysis in one user interface, allowing full control of all 3 methods: intuitive, logical, easy. Trident reflects Seetherm's years of experience working exclusively to provide labs, researchers, and manufacturers with the very best in thermal conductivity measurement. Seetherm's products are globally distributed in over 65 countries around the world, with full local support. Trident. It's better to have options.
Good day, everyone, and welcome to our webinar presentation. My name is Adam Harris, CEO for Seetherm Technologies. Very pleased to welcome you to our webinar presentation today. Hello, Srinivas. Great to have you online with us. Please do make use of the chat box. Say hello. It's a great tool. And if there's anything specific you're looking to get out of today's presentation, it's a great way to interact with us, and we do try to adapt a little bit as we go along with the presentation. Really pleased to welcome you to today's webinar. It is a very well subscribed webinar. I think we had around 250 folks register for this webinar. It's an area of significant interest, and really pleased to have you online with us. So just give me a minute. I'm just going to bring up my slide deck. If you're just joining us, you didn't miss anything other than we just played a short little video that outlines the Trident system. And you'll see some of the technology from the C-Therm Trident thermal conductivity instrument spread throughout this webinar presentation. This presentation is an application-focused webinar. A little bit later this month, we have one more focused on the theory and background of measuring thermal conductivity. But this one is really specific, and it's all about how can we accelerate the thermal conductivity testing in optimizing electric vehicle thermal management. Thermal management is one of the biggest issues when it comes to getting the safety and performance requirements to market with an electric vehicle that is meeting consumer expectations in terms of distance, in terms of mileage, but also in terms of performance, in terms of safety, and overall longevity of the product and robustness. So thermal management really is one of the biggest issues when it comes to EVs. And whenever we talk about thermal management, thermal conductivity is very closely aligned there in terms of really understanding how do we manage that heat that is generated within the vehicle. So today's presentation should run for approximately 1 hour. We will reserve some time at the end of the presentation for a bit of Q&A. I'm just the warm-up act. The star of the show is my colleague, Arya Hakimian. Arya is an application specialist and has been working with many of our clients, many of the top EV manufacturers in the world in supporting different testing and helping them in terms of getting trained on the equipment and how to best to approach the method selection for the different types of materials in EVs. One of the things you're going to see when we talk about EVs is that it's a broad range of materials. So it's not one specific material set. We're talking about phase change materials. We're talking about thermal interface materials, different metals, coolants, liquids, all kinds of different materials involved here in different formats. And that's why this is such an interesting area of discussion, whereas the method selection for thermal conductivity measurement will adapt as you face some of these different scenarios. You know, for example, looking at anisotropy or the oriented type of samples or filled materials with different additives. These require different approaches in terms of the thermal conductivity measurement and the performance measurement. But it's all with a transient class of thermal conductivity sensors that C-Therm really specializes in. So when you talk about thermal conductivity, there's really two broad classifications of methods for thermal conductivity measurement. There's the what I'd call kind of the traditional methods, the old guard. These are steady state in nature. They're very reliable. They're very accurate. They're typically oriented for lower thermal conductivity materials. And the challenge with them is they tend to take a long time to run a test. So, you know, if it's a heat flow meter, it could be a couple of hours. If it's a guard hot plate, it could be a day. If it's a TIM tester, which is quasi steady state, you know, it's close to 40 minutes. So with all these scenarios, it's a fair bit of waiting for the result. And when we're dealing with some of the time pressures involved with electric vehicles and getting those to market, getting some of these problems resolved, some of the quality control and the supply of some of these components, the time to measurement is a very important factor. So a lot of what we're doing in terms of driving value in this space is accelerating the test process, accelerating the characterization of these materials and how we go about that performance testing. So if you're not familiar with C-Therm Technologies, we are a Canadian tech company based on the East Coast. We specialize in this very niche area of thermal analysis, thermal conductivity specifically. And our reason for being, our purpose, our raison d'etre is all about simplifying thermal conductivity testing for the materials of tomorrow. The electric vehicle segment is, I would say, probably one of our most significant trending application areas. It really brings together a convergence of different technologies that we've worked on in different areas. So conductive polymers, phase change materials, thermal interface materials. We're seeing additive manufacturing with metal, something we have some unique background in. All these different types of areas, thermoelectrics, converging into the electric vehicle, which is really exciting and allows us to kind of really create more value add for the client that is facing these challenges. So a quick overview of our product line. I'm not going to talk much about the TX system on the right. That's really more for textiles characterization, although I will just put a comment in here that if you're working on automotive interiors, the thermal touch performance of materials and the selection of fabrics can be very interesting, and quantifying that touch perception in terms of warm feel or cool touch can be very important. So we know that there are a number of automotive interior manufacturers and developers using the TX system, although that's an application that we're not really talking a lot about today. So if you're interested in automotive interiors, drop in a short note in the chat box. We'll be happy to come back to you and talk to you more about automotive interiors. But really what we're focusing today is on the measurement of thermal conductivity. And that's led by the Trident thermal conductivity instrument platform in the middle. It looks like a kind of pyramid shape. This is a new product launched on the market 2 years ago. It brings together the three most prominent methods for transient thermal conductivity characterization. When we talk about thermal conductivity, there's not a silver bullet out there that handles all types of materials and formats: solid, liquids, powders, pastes, conductive materials, insulative materials. You really need a combination of methods to cover those off. And all of those scenarios we encounter in when we're talking about an automobile. So it's important to have some different tools at your disposal in terms of effectively characterizing the thermal performance. But all of these are transient in nature, which typically means they're fast to run. We're talking a test on the order of a few seconds. So very, very quick test time featured in all of those techniques. We'll detail a little bit further some of the methods specifically, but the little steel cylindrical shape in front of the pyramid, that's the MTPS sensor. It's the only single-sided method for thermal conductivity measurement. It's really a very good, accurate one, simplifies the measure a lot, great reproducibility. And one of the really interesting applications for it is thermal mapping. So if you're dealing with additive material, with composites with additives in them, this is a great way to look at, for example, the homogeneity of that performance. Often we see settling or agglomeration occurring, and this is a great way to pick up some of that variation. I think Arya is going to talk a little bit further about that in his presentation. In the middle, you have that needle-looking device. That's the transient line source needle probe. This is for polymer melts, really sticky situations. It's sheathed in stainless steel, so it's very, very robust. To the left of that, you have an example of our Flex TPS sensor, sometimes called a hot disk sensor. This provides flexibility. It's a flexible sensor that gets sandwiched between two samples. So it's a very flexible one, but it's also giving the user flexibility over the experimental parameters in terms of test time and power applied, and gives you a little bit more latitude in terms of how you want to set up your measurement, but it is oriented towards a more experienced user. It unlocks some powerful capabilities with that. You have some specialty utilities available with for thin films, for anisotropic materials, sheet metals, some really interesting capabilities, but it comes with a requirement for a little bit more user training. On the far left, we have our more economical offering. So Trident is a research grade instrument, very powerful. It's not an insignificant investment, but it equips your lab with really a premier instrument in terms of thermal conductivity characterization. The other end of the spectrum on our product line is the thermal conductivity kit. And this is really more just about getting in the game, so to speak, in terms of measuring conductivity. It's often used in academic settings where budgets are very tight, or if you're bootstrapping a new startup, maybe trying to accommodate some measurements from home or from the garage. This is paired with a Keithley power source measure unit, and our software installed on a laptop provides full data acquisition and regression analysis, includes a sensor, a reference material. Pairing it with a laptop and a Keithley meter, everything you'll need to establish a basic functionality in terms of measuring the conductivity of solids up to about 60 watts per meter Kelvin. If you'd like more information on the Keithley kit or with the thermal conductivity kit, I'll ask my colleague Anna, who's moderating today's session, to drop in a link in the chat box. Anna is a member of our business development team. She's a regional manager for Europe and Latin America. A delight to work with, and I'm very appreciative for Anna's help in putting this webinar together and helping moderate today's session. So I talked a little bit about Trident and the combination of those three methods. So it's really one instrument with three methods for thermal conductivity. In our view, that when it comes to thermal conductivity, it's really important to have options. I really like this quote from Abraham Maslow. If you've seen my presentations before, I think I repeat this a lot. I find it really represents and captures. It speaks to the value proposition of Trident. And it's really that when we talk about thermal conductivity, when all you have is a hammer, if you only have one tool in your toolbox, everything looks like a nail, and you end up force fitting it into areas of application where it is not ideal. So really the value here is giving yourself and your lab the future-proof capability to deal with pretty much any situation, from solids to liquids, etc., all those different types of materials that you may face in your lab. These are some of the different sensors available. You can see the needle probe here on the top right, just to give a bit of sense of scale and minimum sample volume requirements. The active area of this is about 150 millimeters, so it will require among the larger sample volumes. Opposite end of the spectrum is a single-sided sensor, MTPS, with an active area of about 18 millimeters. That's roughly the size of a US nickel coin. Offers among the smallest sample volumes. The Flex TPS sensor in the middle is available in different size formats. That's 6, 13, and 30 millimeters in size. Some different accessories available. The liquid and powder cell in the top left and lower left, the high pressure cell. I see some folks online that are involved in hydrogen research. Our unique capabilities with our high pressure cells and being able to measure conductivity and integrate our sensor in those cells is of direct benefit to hydrogen researchers, where the kinetics of how those materials perform is related to the effective thermal conductivity of the material. But one thing we really need to be talking more about in industry is that when we're measuring conductivity, that we're measuring it under representative conditions. That could include humidity or temperature, but it also matters what pressure we're testing at. So if your material is going to be under a specific atmospheric pressure, it's best to test it under those conditions to truly get a representative value for how that material is going to perform. If you densify a material, for example, you'll typically cause an increase in its effective thermal conductivity. We have special gauges, our compression test accessory in the lower right, to control that very precisely. So if you're working on a gap pad material, for example, this is very important because with a gap pad material is a thermal interface material. If you apply a lot of pressure on it, it's going to push out any air voids. If it's a filled material, it's going to improve the connection of the additive. It's going to bridge the bond line better. You're going to have a much better effective thermal conductivity on the material. But it's really important that it's representative. So, we've seen examples where results have been presented and they look phenomenal, but when you go into the details of the gap pad of how it was tested, it might have been done with 1 ton force. if you're looking at applying that type of force in your electronics package, that's fine. But I think you risk, in a lot of cases, misrepresenting that real performance. The next slide here just gives you a sense of some of those different accessories on the Flex TPS. Top right, you see some of the different size sensors available, the TPS sample clamp, the powder cell, and the high temperature sensor available there. I want to just take a moment to speak to those special utilities available with the Flex TPS. There's the slab TPS utility. So if you're dealing with aluminum sheets or different highly conductive metals, the slab gives you a great solution. Instead of applying a transient method, which typically requires for the duration of the measurement that heat that's introduced with the sensor stays within the boundary of condition of the sample. Well, that condition can be avoided with the slab method specifically, with that utility where you'll input the thickness of the material. And it just gives you an effective way to really deal with high conductivity sheet material. The anisotropy utility, great for oriented materials and thin films. We know, of course, in batteries, the separators and some of the other encapsulation materials, it's very important that we have a way of understanding the conductivity of the thin films themselves. A lot of those used in this space, so a nice capability there. So in introducing these different types of methods, one of your challenges will be, well, how do I know which method to use where? And the method selection guide pictured here was put together a few years ago by our group in consultation with some external consultants and experts in the field. It is a nice comprehensive resource for identifying what is the optimal method selection for your application area. It also includes coverage of other areas of thermal conductivity characterization, such as laser flash. If you're having to measure at 1,000 degrees Celsius, it's a pretty short conversation in terms of the available methods. You're going to need to use laser flash, but I wouldn't suggest using laser flash on a filled composite, anything that's anisotropic or a liquid. This is where we often see a lot of bad data come out. So it's really important to understand how these tools work, these methods, and where they are best applied in terms of materials. And this method selection guide is a great early resource for that in mapping some of those areas. Free to download. I see Anna has already dropped that in the chat box. I want to reference just in passing some of our cooperation partners. We work closely with a couple of world leaders in material characterization out of France. We've developed some very close relationships with Ceteram Instrumentation. They're experts in calorimetry and thermal analysis, such as TGA, DSC, DTA, etc. And also Metrovib. Metrovib has the most impressive DMA product line. They've got some really cool robotics with their expander platform. Used a lot in the tire and rubber industry, but also very applicable in composites, thin films, and so forth. Wherever you have vibration or this kind of oscillating force load on a material, DMA is a very powerful platform. And if you're interested in DMA, just similarly, enter a short note in the chat box. We'd be happy to follow up with you in providing a further introduction to some of those methods, or to introduce you to some of our partners at Metrovib and Ceteram. All right, just a couple of quick, bit of sharing in terms of our customer and their experiences with Ctherm. There is a link that Anna will put into the chat box of where you can view, I think 50 or 60 different client testimonials. But just to give you a kind of sense of where clients find the value with Ctherm and what they're doing, some notable brands here. So NASA, I think everyone understands what that organization does. Very impressive group to be working with. Dr. Jackson just commenting on how fast and easy it is to operate. Our systems provide unequivocal results. 10 out of 10, extremely satisfied with that investment. The next one is Haydel Composites out of the UK. So they do a lot of specialty composites for the automotive sector and other high performance applications where the heat transfer is a very important characteristic in terms of how their product performs. Now, these are filled materials. So one of the really interesting things here is the thermal mapping that they're doing with the sensor, so they can really be assured that the fillers they're using are well distributed. That's so important from a performance perspective. And a nice just general reflection on what a key piece of testing equipment it has become at Haydale, offering that fast and accurate thermal conductivity testing. And then the last one I'll just highlight here, and it's a quick highlight, is from Covestro. That's formerly Bayer Polymers in Germany. Just talking again about how fast and accurate the capability to measure thermal conductivity of their polymers. They're using this both with the MTPS method, which is providing that quick and easy reliable measurement, but they're also using the needle probe for some of their polymer melts. So it just speaks to that value of having a few of those different methods available. Now, as I introduce this, my colleague Aria, who's really going to take the reins here and do a deep dive on looking at how C-Therm is helping accelerate thermal conductivity characterization across a broad range of materials involved in the development of electric vehicles. I just wanted to talk a little bit about why speed is so important and the pressure we're all feeling to quickly get to market. So this is a little bit different than a lot of other application areas where we work with manufacturers, with other technology companies, and it's a very iterative process. It's a methodical process. Yes, there are pressures and there are improvements, made in a wide range of these areas, but this feels very different when we talk about electric vehicles. The pressure here, I think, is immense, and it's really important to understand what is happening with the disruption in the automotive industry. I know a number of you are, this will be like preaching to the choir. You're experts in this field. I'm sure you've been talking about this for much longer than we have. So I'm just taking some of the lessons I've learned from you and trying to present them here to a broader audience and promote this thinking. But I think it's really an important part of when we talk about electric vehicles, the pressure and the disruption that's underway. So it's very much an S curve that we're seeing, I think, here emerge. And that comes from the convergence of different technologies. And it's different than what we see in some other areas of product development and adoption, where it would follow a more kind of linear progress or a normal distribution in terms of capturing market share. When we talk about this type of scenario, which is, I think, really in automotive, we're talking about an event that's once in 100 years in terms of the significance of the disruption. We're really looking at this resulting from the convergence of many different technology areas into a product that's emerging on the market in terms of availability, and has been for the last several years, is viable and is meeting those performance requirements. But we're bringing together phase change materials, electronics, a bit of thermal electrics and energy harvesting. Battery is at the core of it all. And of course, the traditional elements of the automotive vehicle. And we're really putting all these technologies together, and it's the convergence of those that's very exciting and very challenging for us as manufacturers. So I just wanted to talk a little bit about that and how we often underestimate the pace of change that's happening when we talk about converging technologies. There's a couple of nice examples, and I can't claim this is an original thought. I am sampling from other thought leaders that have already spoken on these issues, but I'm trying to share it because I think it's an important part of understanding what we're trying to do here. So there's a nice example here from AT&T back in the 80s. Hired McKinsey and Company. I'm sure you're familiar with McKinsey Consulting. I would suspect millions racked up in trying to develop a forecast of what will the cell phone market be, the market for mobile phones. What will the adoption be by 2020? And after a lot of careful research, variety of techniques, they come up with a number of about 900,000 subscribers. And I think that is for the US market. They were off by a factor of 120. Okay, it's a massive miss. But it's the difference of thinking about adoption in a linear way versus the S curve that we're seeing when we talk about the convergence of technologies. And really, I think if we think back in the automotive sector itself, we have seen this. It's just we saw it about 100 years ago. So I think, and I'm going to approximate here a little bit. History was not my forte, but around the late 1880s, you see, I think, consensus around the first automobile really being available or invented. And then it's about another 15 or 20 years before we really see, kind of wider scale adoption. So it's kind of interesting if you think of electric vehicles and some of the early introductions in the, over, 2005, moving forward. They're there, but you're not seeing that adoption in a mass scenario. But what's really interesting in this observation is just how fast it flips. It's like a light switch. It goes really quickly once it hits that kind of inflection point. And so there's this really interesting example provided of looking at New York City. Fifth Avenue, circa 1900. So this would be about 12, 15 years after the invention of the automobile. And if you look on this street, a very modern city at the time, you see all these horse and buggies, but you can pick out maybe one automobile. And then if you fast forward to 1913, so in 13 years, I just want you to reflect on the significance of that pace of change. And you look at the streetscape. It's very difficult to pick out a horse and buggy. They're almost all automobiles at this point. And so it's a good example, I think, of what we're seeing with the challenge of bringing electric vehicles to market, that we've hit the inflection point. Just an interesting anecdote. This morning, a friend called me and it was talking about going to buy a minivan. He's got a young family, needs a bit more room, and he's decided not to buy the vehicle. He's going to lease it. And I asked him why he's doing that. There could be good reasons to lease a vehicle, but he said, we don't have an option in our local market right now to buy an electric vehicle, but I think there will be in 2 years or 3 years. And so I'm going to put off making a long-term investment in the combustion vehicle with an intention of swapping in an electric vehicle here in a few years. So, it's very anecdotal, but if you look at the history, if you look at the experience in terms of adoption and just the general sense of the market, we've hit that inflection point, and we don't probably have as long as we think. If you're one of those horse and buggy producers in 1900, I don't know how many of those survived post 1913. I think they probably thought they had time, that they were on a slow decline, but that they would sustain, themselves in a gradually reducing market. And I think what really they found is it was like somebody just turned the lights out on them. And so that's the pressure we're dealing with here when we talk about getting to market with a product that works, that has the safety, that has the performance range, all those things necessary to be successful in the electric vehicle market. So I want to introduce my colleague, Arya Hakimian. He is a brilliant young fellow, application scientist here at C-Therm. Works a lot with clients in this space. He's going to be highlighting some different work that's been published and some of the work that we've produced internally and giving you a full picture, a survey effectively of all the different materials that are involved in electric vehicles and why and where the thermal conductivity matters. So with that said, Aria, I'm going to stop my deck. I'll take this off screen and I'll invite you to take the stage, center stage, the star of our show, and please take it from here. I'll rejoin everyone for the Q&A session. Look forward to the presentation. Thank you.
Awesome. Thanks, Adam. Hello, everyone. So as Adam mentioned, really, I'll be taking over from here and diving into some examples about the accelerated thermal conductivity testing in the electric vehicle space as it relates specifically to thermal management. We'll start out with some kind of high-level discussions, then go into some more particular examples throughout the session. So just kind of a few screen grabs to get your attention before we get going. And again, coming back to the aspect of thermal management, electric vehicles are in market right now. A lot of folks that I know actually have become some of those early adopters, but that's not to say there aren't challenges still. There are reports semi-frequently of these issues, fires. So they're not fully optimized quite yet. There are some, we'll say, kinks that need to get worked out, and we'll be discussing those today. Kind of a little fact that we pulled here on electric component failure, just to address the fact that temperature accounts for about 42% of the faults that occur. There are other aspects, vibration, humidity, and then some others that aren't listed. Of course, it's a multifaceted issue, but again, temperature can be viewed as being at the core of some of these issues. So we're talking about thermal management and issues surrounding that. Really, this can come back to a process called thermal runaway. Essentially, this is where you get an increase in temperature through some sort of reaction that introduces heat to the system, which furthers that reaction. And if you do not have adequate heat escape, whether that's through the process, the materials, cooling systems, whatever that may be, you can get stuck in this feedback loop. And if unchecked, this can result in what we would describe as a destructive event. So just kind of an example here, thermal runaway in a lithium-ion battery, just demonstrating the process. You can see that starting out at the top, image A, heating, there's no issues. B, there's the safety venting. C, get gas release, but through some process here, there was not able to have adequate release. And then we see throughout D, the thermal runaway event begins. And this leads to an ignition, combustion. You can view that as the destructive event. And then obviously at a certain point, it will be self-extinguished, but obviously now the battery is damaged. Thermal management also relates to performance. So, thermal runaway is a major safety concern, but the aspect of the performance of an instrument or a device can also be heavily impacted if it is not being accounted for. You can see here just a quick graph. Maximum charge as a function of cycle temperature. So how often again, this is a lithium ion battery, how often it is cycled and at increasing temperatures. And you can see effectively that over the lifespan of more and more cycles, you get an overall decrease in performance. So again, whether you're looking at it purely from a safety aspect, a performance aspect, thermal management is really front and center for these emerging technologies. So how do we cope with this? How do we effectively reduce these risks? Well, essentially your thermal management can come in different forms. There's passive, active, hybrid cooling techniques. I'm sure we're familiar with heat sinks, thermal interface materials, forced air intakes, things like this. But regardless of the type of management that is being introduced, really the components material selection is going to be very heavily weighted here in the overall performance attribute. Whether that's of the pure system itself, of the cooling system, or both, material selection is going to be very important. And from our perspective, and again, what we'll be focusing on today is the material selection from the perspective of thermal conductivity being the key design metric. If you're not familiar with thermal conductivity at a very high level, we're simply inferring the property that dictates a material's ability to transfer heat. You can see that thermal conductivity has units of watts per meter Kelvin. And this comes from the measure of thermal energy input in watts across a given thickness at a given temperature difference, so watts per meter Kelvin. And really, again, this is what we'll be focusing on fairly exclusively here today. So when we look at, call it the anatomy of an electric vehicle, Adam alluded to this earlier, but it's such a vast group of materials. Looking at perhaps the battery packs themselves, you have PCMs, thin films, various pastes, fluids. Looking at the automobile chassis, I mean, this is still coming. It's a new emerging technology, but it's still built on the automobile skeleton. You have, ceramics and metals in your brake pad systems and the metal chassis, various polymer composites throughout. So it's really truly a wide-ranging material type in this field, and having the proper tool for analysis when it comes to the thermal conductivity is going to be very important. And again, Adam really covered this well earlier, so won't be spending a lot of time, but just to highlight here, transient methods for thermal analysis have some really key benefits when we're talking about not only the versatile sample type, but really the speed of analysis, very flexible sample sizes. And again, our three main methods of discussion here today are the modified transient plane source, MTPS, the transient plane source, TPS, and transient line source, TLS, all of which are available on the Trident platform. So I figure we jump right into some examples. There will be some in-house data that we have collected and others like this where they are various academic publications. We'll take a dive. This first one is looking at battery thermal management systems. This is from joint work coming out of Canada and the US. And really in this study, they're aiming to moderate temperature by developing a battery thermal management system, or BTMS. Again, these thermal management techniques, coming back to those previously mentioned options, can be active, passive, or hybrid techniques. And in this case, the group decided to move forward with PCM, so phase change materials, as a form of passive cooling. Now, when we're talking about PCMs for batteries, there are some, very specific challenges that can be faced. If you're just talking about a pure base PCM, generally they're not going to be sufficient alone during, aggressive operation. When you really push those temperature limits, they have a certain point of diminishing return. Certain properties such as unfavorable thermal inertia, limited available latent heat, and again, what we'll be focusing in on is that low thermal conductivity. So what this group proposes a solution, which you'll see a lot of groups working with these additives, is adding a material to that PCM to enhance the effective thermal conductivity and ultimately improve on the temperature regulation properties. I just put this little image here of the MTPS. This was the device used in this study, and whenever we talk about PCMs, it's really important to note that, if you didn't know, phase change materials, we're referring to something that can have a change of phase, so perhaps going from a solid to a liquid. Not all measurement techniques are appropriate. If it's appropriate for a solid, it may not be appropriate for a liquid, and vice versa. But with the MTPS, it's very versatile, can handle solids, liquids, powders, pastes. It's really great for this application space. But how you'd actually go about testing a PCM, let's say in its solid form, you would place it on the sensor, and then if you bring it through a melt point, you can see there's the liquids and powder cell on top of the sensor, which is used to contain the non-solid material. So a really great option for testing completely through the phase change of a sample. So just looking at some of the results that were obtained here, we can see from the graph on the left, or table on the right, compared to the pure wax, so the pure PCM that was used, again, fairly low thermal conductivity as was expected across the full temperature range. But you notice that by increasing the additive or the filler material here, you're noting a fairly significant increase in thermal conductivity going from 5 and 10% loading. You do notice that as you also analyze this data as a function of temperature, in its solid phase, we're getting a very distinguishable difference, but important to note that when you do approach that liquid phase, that transition of phase here, you do start to see some, I'll call them diminishing returns at the upper end. And again, this is simply related to, you can imagine a solid material has really good conduction pathways. As it becomes more of a liquid state, the disorganization of that matrix has an effect, quite notable effect on the effective thermal conductivity. But really here, they were able to show that the average temperature of the system was much lower when you added in that additive to the base PCM. Also looking at it in the sense of increasing PCM layer thickness, you note that the average temperature does show a steady decrease with PCM layering related to the increased additive that is present. So ultimately what they were able to conclude, taking this data, going in through some simulation studies, is the PCM can maintain a temperature about 1.2 and 1.9 degrees lower compared to the control at the 5 and 10% weight loading, respectively. Ultimately, this all comes back to the improved thermal conductivity of the filled system. So really just demonstrating in a very simple sense here that the effective thermal conductivity can have a very large impact on the overall temperature that will be imparted into your system. So when we're talking about PCMs going from that solid to liquid phase, whenever we're talking about a liquid form or a fluid, it's really important to just add a quick note here on convection. Convection can be a main source of error for a lot of liquid testing. It is something that's fairly well known in the industry, and it's something that you need to take into account. The best ways to negate the impact of convection, there's a few approaches: reducing the total volume, using very short test durations, or low energy impulse or a pulse measurement. So decreasing the total delta T that's introduced to the system during your measurement. With the MTPS, again, this is one method that we kind of focus in on a lot because it has some really great advantages here, particularly to liquids and the, particularly non-viscous liquids. Your standard MTPS test duration is about 1 second. So you can see that having a very short test time has quite a few benefits, being a non-destructive method, and in this scenario really reduces, or I should say completely avoids, the introduction of any convection in your media. If you were to increase the test time, and you can kind of see this simulation that was performed at about 5 seconds, 11 seconds, you start to see more and more of that convection wave build. And then when you're analyzing kind of on upper end of around 14 seconds, which granted isn't that long of a test time, you do notice these quite large convection errors that can be introduced. And if you look in the literature and standards for other methods that deal with liquids, some of them state test times even longer than this. So it's something that you really need to take into account when you're designing your testing setups. So just a few takeaways here. I personally work with quite a few groups that are dealing with, these advanced materials, finding the best ways to test them. And, I always try to impart a few kind of tips and tricks on how to best analyze the data, but also how to report it. It's really good if you can take a look at not only just the final value that you're getting, but also some of the more particular information from the test, perhaps the temperature versus time plots, residual error plots. These can show signs of convection errors that may not just simply be present or I'll say obvious in that final value. When you're reporting these results, whether it's for internal companies or if you're a lab doing these reports for other groups, and taking note of the test time, the applied power that was used, even the sensor probe and dimension, These are things that can be really important to take note of, because if you're not reporting these, sometimes it can be really hard to compare your results, especially if you do get discrepancies between different methods and different groups. So having as much information available to you is going to be always the best tool that you can use. So kind of continuing on just the aspect of liquids testing, Adam mentioned earlier, and it made a really great point, that you not only want to get good data, but you want to test in a way that is representative of the in situ or real world condition. So, one example you might think of is a cooling system, a closed system that has a liquid inside of it. If you're increasing the temperature of that system, you're most likely changing the partial pressure inside. So having an understanding of how the properties trend as a function of not only temperature, sample format, but pressure can be very important in some of these scenarios. One option that we offer here at CTherm is these high pressure cells. They have the same MTPS technology that we've talked about in kind of more of the base configurations, but giving you the added capability to test under varying pressurized or gas environments. And again, really all this does is give you the ability to fine tune your testing to be truly representative of the end use condition. We see here just some example data collected with the MTPS high pressure cell on a Duratherm material. This is a heat transfer fluid. You can see the trend in thermal conductivity as a function of temperature. Really good agreements with the measured and reference values, but just noting that the pressure of the sealed vessel was introduced in this testing. So we made note of that pressure and continued with the analysis under those representative conditions. And again, if this was something that you're just testing in the ambient atmosphere, other issues can come into play as well, but also you may not be getting truly representative test data. So going into another example here of some work done in academia, enhanced thermal conductivity for nanofluids, and in this case looking at silver nanowires as the additive, but taking a look at how different shapes of your additive can come into play. And this is some work coming out of China. So we take a look in this study. Really, their goal was to increase the thermal conductivity of the HTF, the heat transfer fluid, using a conductive additive. But again, really making note here of the effect of the different shape of that additive. So it's the same material, it's a silver nano particle, but in different size and shape formats, as you can see from the SEM images at the bottom there. So what they found from their results is essentially, as you would expect, the higher volume fraction led to a higher effective thermal conductivity measurement, so a greater enhancement of that thermal conductivity. But also the effect of the aspect ratio, or the size of that additive, was rather significant. They noted that the higher aspect ratio sample also had a general higher thermal conductivity compared to the one that was lower. So even though it's the same material being added, size, shape can have a very drastic effect as well. And then here a note on investigation of thermal conductivity of carbon nanotube reinforced composites. So this is coming out of some work out of Europe and Romania and France. So if we take a look here, this is kind of diving into some more, I'll refer to as traditional automotive components. So, rubberized tires. And in this study, it really relates to this because, the wear and tear on a tire can be directly related to the thermal stress under the active use. So the study really aimed to improve that effective thermal conductivity to reduce that thermal impact and, in one aspect, improve the longevity of that material. So these investigations were done on different loadings of carbon nanotubes into the composite matrix. So the rubber was impregnated with CNTs at different weight loadings. So you can see 5, 10, 20, and 30%. Again, based on the SEM images here, the CNTs may be more pronounced at the upper loading. But really what they found was, again, as you would expect with the higher loading of the CNT, this resulted in an increased thermal conductivity. There's about a 26% improvement at the 30% loading compared to that control. And again, noted that this material was evenly dispersed throughout the matrix. So if you do have good control over your dispersion, that is going to be very important for getting those quality and those absolute accurate measurements. But again, what we see here is just this, the story that we see quite often is introducing more of that material will increase the effective conductivity. And there are granted other properties that will change with different weight loadings. But again, definitely from the perspective of thermal conductivity, we see that net improvement. So we talk here about these additives in these fillers, and Adam alluded to this earlier, surface mapping, filler detection. This is something that we've brought up a few times in some previous webinars. If you'd like to learn, kind of dive into it more, some of the previous webinars that were posted really go into this, and we also have some additional resources if that's of interest. But with the MTPS, you get a really great additional measurement tool in your toolkit, and that's the ability to map out the surface of a sample and perhaps detect if you are getting any localized agglomeration or buildup of that filler. So in this rapid screening approach, you can see in this, just kind of this example here, we had an epoxy resin with a conductive metal nanoparticle added, and you can see it was done on purpose to be non-uniform. So visibly, we could tell that this sample is non-uniform. But to help illustrate the point for examples where maybe the sample that you're working with isn't visibly detectable, maybe it's an opaque material that you can't see the filler. The way to actually detect this type of measurement can be done again with the MTPS by doing these rapid screening measurements at different surface locations. And what we were able to show is, if you can see those measurement locations labeled 1 to 9, we see areas that had some very higher filler concentrations, such as location 3, resulted in one of the highest effective measurements. Whereas, and as by example, location 2, we can see much lower filled, less of that filler in that area, had a much lower value. So whether you're looking to get that absolute quantitative measurement or maybe more just a rapid screening tool, the MTPS can provide you with some really powerful options here. So taking a little pivot now into TPS, the Flex Transient Plane Source. It has some really great applications in this space as well. One of which we'll take a look at, called more simple measurement approach, which is the bulk configuration on brake pads. So importance of brake pads, if you've been in the automotive industry, you know that brake pads really going to be crucial from a thermal aspect with respect to the stopping power. So how efficient that brake pad is at slowing you down can be really directly related to that thermal property. Traditional brake pads used to be made of just pure metals. Obviously, those are very heavy with the ever, increasing improvements to make lighter, easier materials. Really, they've started branching into different material types. So there's semi-metallic, ceramic, non-asbestos organic or NAO, and low metallic NAOs as a few examples here. So depending on what type of brake pad you're using, you may have different thermal performances, and these different materials come at different price points. So in the example that we're looking at here, some results on testing both a semi-metallic and a ceramic brake pad. The semi-metallic was much cheaper, ceramic was a little more expensive. But what we actually saw from just a thermal conductivity perspective was a much better performing brake pad that was actually cheaper, looking at the semi-metallic component. Now, again, there's various other aspects here. If you're a car enthusiast, you know about the noise your brakes can make, the dust buildup. There's a lot of aspects here that need to be considered. But from a thermal management side of things, we can see that throwing more money at something doesn't always necessarily yield, I'll say, better results. So another use of the TPS sensor, specifically looking at the anisotropic utility here when it comes to polymers. This is something that we've seen across quite a range of application fields in recent years, but again, very applicable here to EVs as well. Finding a way to really test that directional dependent material type. So just as a quick overview, isotropic versus anisotropic materials. Essentially, anisotropic are those that have a directional dependence to them. So if you take a look at that cube with the X, Y, and Z axis, an isotropic sample is one that would be the same thermal property in all directions. However, if you had something that was anisotropic in nature, you may have differing in-plane and through-plane thermal conductivities, or even in some instances, depending on perhaps if it was an additive manufactured printed material or just some filler, you can have samples that are fully anisotropic, or where your X, Y, and Z direction are all different from each other. So there are certain limitations to the TPS method. You are limited to those that are orthogonally anisotropic, so your in plane can differ from your through plane. If you were dealing with something that was fully anisotropic, just as a note, this is something that you would need to test exclusively with the MTPS sensor, and definitely happy to follow up with anyone that may have questions on anisotropy. But again, we'll take a look at some data that was collected here. Again, just some simple examples, and in some instances, the difference between that in-plane and through-plane direction can be somewhat, viewed as minimal from the example of this sample on the left, or it can be more pronounced, looking at the example on the right. But in either case, the TPS anisotropy utility it's a great measurement tool for these types of samples, and it can provide you some really, really important information with respect to the directionality in the samples that you're working with. And another note on one of the other advanced utilities with TPS is looking at SLAB. So Adam mentioned earlier, SLAB is really great for thinner materials, really metallic sheets as an example, or an emerging market that is really great for this measurement technique. Essentially with SLAB, it follows the same measurement principles, but you get a slight difference with the thickness requirement. So in this example, we were testing some aluminum sheets, about 1.75 millimeters in thickness. It does require a slightly specialized test setup compared to your base TPS measurement. You actually have an insulative backing layer on the top and bottom of each sample. In this case, we're using EPS foam. But again, looking at some of the results that were obtained on this grade of aluminum compared to the reference value, conductivity, and also diffusivity, well within what we would expect with our final measurements here. So there are certain instances where these, metallic materials have a limit in your sample thickness, maybe makes them non-viable for other measurement techniques. And again, the whole idea here is it's really good to have options, and transient will always be amongst the fastest measurement tools, especially when you're dealing with this type of market where speed is of great importance. And a last look here on one of the final utilities with TPS is thin films testing. In electronic vehicles, thin films are seeing, in various parts, kind of in the battery separators, as was mentioned earlier, different polymer-based films. And thin films introduce a somewhat challenging sample format for certain methods, really just related to the fact of the sample requirements that are sometimes needed. But again, with the TPS thin films utility specifically designed for thin films down as low as about 10 microns, this is something that can be used for this type of analysis. Your thin films testing procedures, it's a little different from what you might view as a traditional TPS test, but essentially involves this layering of the thin film, upwards of 2 to 3 total layers with a singular or a common backing material. And again, here what we're varying the thin film thickness to increase the insulation component of that temperature change. And in this way, the software is using that information to, again, determine the thermal conductivity of that thin film. So it avoids the use of perhaps maybe needing to layer up dozens and dozens of films to create a sufficient sample stack. Here you can get away with 1, 2, maybe 3 layers of film, and it's a great option, again, when you're looking at that pure thin film measurement. So just some results that were obtained here, some kind of known materials, Nomex paper, Kapton, Mylar, different types of these polymers, again, showing really great agreements between the measured and literature values for those samples. And finally, one that's not talked about as much, again, the TLS, the transient line source. But I do just want to have a quick note of it here today before we wrap up. Again, really great for those viscous liquids, polymer melts. Convection errors are most prominent in thinner or lower viscosity materials, so always best tested with MTPS. But if you're dealing with samples that are thicker, and if you kind of look at the viscosity range here, so anything above about the 50,000 centipoise range, kind of looking at the example, like just anything ketchup or above, if you can imagine ketchup as the consistency of reference here, these are types of materials that are really great for TLS. Also appropriate for MTPS for sure. However, depending on the chemical composition, the type of a material that you're dealing with, again, TLS being completely coated or sheathed in stainless steel really makes it a great, robust option. So just looking at some test data here, this was done on a polymer melt. You can see that, again, polymer melts are, really kind of more nasty samples in the sense of, removing that and cleaning it off a sensor. If your sensor is completely coated in stainless steel, you really don't have to worry about it too much. And again, giving you that elevated temperature capability to see how that material changes as a function of temperature. So just some really, conclusions here. EVs, as we've kind of run through here today, incorporate such a wide range of materials. There is no one measurement technique that can do it all. So again, having access to those different options really give you the best chances of getting those accurate and valid measurements. And the speed of analysis, this is also really crucial. As mentioned, transient is going to be the fastest possible measurement technique to get these results. And as Adam alluded to earlier, if we're dealing with a significant change that's going to occur over the matter of years, every second counts. So whether you're dealing with an emerging material, R&D development, whether you're doing product testing, QA, QC, speed is going to be really of importance here. And this is why transient measurement techniques are really going to be a great fit in this type of market. Just as a kind of a final note, some additional resources. I know Anna's been posting some throughout the presentation here today, but just in general, on the CTherm website, we do have the full library of previous webinars, again, covering quite a range of topics. Definitely feel free to go take a look at those. We also have a quite extensive tech library. I see Anna just kind of posted in the chat there for our resource page, application notes, papers, different, topics, a lot, again, on EVs. You can find plenty of those there, but others of interest as well. Really just wanted to highlight the fact that, we're here to help, and we have resources available to do that. So from my side, I'd just like to say thank you. If you did have any questions in particular, I know we're going to open up a Q&A here shortly. My email is right on the page there. If you did have anything that you wanted to speak with me directly about, always happy to discuss those with anyone that's interested in. Also, feel free to reach out to me on LinkedIn. Happy to continue those discussions in either platform. Also, just as a kind of a more formalized next step, we do offer video demos. If you wanted to reach out to us, we can set up a time where we can actually show you the different sensors with different samples, run through some testing, talk about the software and how that can be done. We may be able to set up some complementary sample testing if this is of interest. And obviously, we'd always be able to provide quotes for the Trident platform if you're looking to bring something in-house. There are one upcoming webinar scheduled for this month here, Innovations in Thermal Conductivity Testing. Just as a note, this will take more of an approach, not necessarily application specific, more of a general overview of our different methods. It is slated for more of our Asian Pacific time zone. If it's something you're able to make, or maybe you have colleagues, definitely feel free to invite those there. And obviously there will be other additional webinars coming up in the future. So with that all being said, I'll end my portion here. I'll throw it back to Adam and we can jump into the Q&A section.
Excellent. Wonderful job, Arya. Thank you very much. A very excellent review on all those different materials in electric vehicles. So at this point, I'm going to stop the recording and we're going to move on to the Q&A portion of it. But just as I sign off on the recording, I want to thank everyone for taking the time to sit with us and the interest you've shown in this topic area. We'd really like to move this more towards a dialogue. That's where we really get excited, is talking to clients about the specific challenges and opportunities for measuring thermal conductivity and where it's important, how best to proceed. So do certainly feel encouraged to reach out to us. There's a variety of different channels to do that. If you would like a quote, I encourage you, even if it's just for budgetary purposes, there's no high pressure here. If you just like a budgetary quote for next year's CapEx, something to keep in mind. It's an easy way to just get a quick estimate back. It is a modular platform, so it does depend a little bit on the range of materials you're looking at, but great way to just get some budgetary numbers in. So at this point, I'm going to stop the recording and we'll move to the Q&A. Thanks, everyone. Stay on the line for the Q&A session.